Thanks. So thanks for being here, but I do have to start off with an apology. So Steve Oney should have been the one who is presenting this work, but unfortunately got stuck behind some... Then the mic was better? I don't know which. This one's on. Yeah. That one's on. All right. Great. So Steve Oney should have been the one presenting this work, but unfortunately got stuck behind some last-minute passport issues on the way here. And I say I have to apologize because about a year ago I tweeted this, and since then there have been, this is my third presentation that I got within 48 hours of having to give it. So we're going to do the kind of experimental version of this talk, but all credit for the slides and much of the awesome work here goes to Steve. So, and sorry, I just realized this is not showing me the right view. There we go. All right. So today I'm going to be talking about a shared browsing architecture that, among other things, will allow us to bridge some of the most significant web accessibility gaps that we encounter. And talking to many people, including some reviewers from other conferences, especially beyond the accessibility community, I realized that some people wonder if this is actually already a solved problem. And that's not wholly unreasonable, right? You might think that, sure, there are probably some websites at the corner of the internet that are basically one big image. But other than that, this must be solved by now, right? And the answer to that, to keep it a little bit concise, is no. To dive into that in more detail, not even close, it turns out. So why is that? We're not even going to solve it with this paper. I'm going to show some work I'm personally really, really excited about on how to make it better, but we're not going to solve it. But how come? Well, it turns out it is just really, really easy to write inaccessible web pages. So let's look at why. This is where I give the thumbs up for audio real quick.
Visited, link.
So this is what you see if you are using a screen reader to navigate the web.
Learn more.
So you tab through elements. Good with the audio. You tab through elements, and you're able to select certain parts of the web page and interact with just those components. Now, this is pretty reasonable for websites that have links that you need to click with proper text descriptors. But it turns out that it's really easy to create content that's not visible to these screen readers. So we will see an example here. So this is a restaurant. It looks like a perfectly reasonable menu. It's mostly a text web page, so this should be a little bit simpler to use with the screen reader. But actually, there is information that is encoded visually. So the fact that red indicates spicy is not something that the screen reader is going to pick up on. So again, this constitutes an accessibility gap. Now, you're probably thinking, great, you found some random little restaurant that didn't have a fully accessible page. Surely the web program for one of the premier HCI conferences, which, by the way, has an accessibility track and includes many blind attendees, wouldn't make the same mistake of encoding information in an exclusively visual way, right? Like using an unlabeled image to represent award-winning papers. Oops, but it does. All right, so here's another example of what can go wrong with a screen reader. So here's another restaurant web page. And when you try to order carryout, it actually shows this little calendar select menu, but each of those elements is actually a div. And the div is not going to be usually something that we can think of as an interactable element in and of itself, so the screen reader skips right over it. So nothing in the selectable calendar is actually seen by the screen reader. Okay. Now, you may think that surely the web program for a different HCI conference, maybe one we're at right now, wouldn't make this same mistake and use div elements for things that are essential to click on, like arrows to expand the individual session information. But it does. And by the way, this same problem comes up for the Chi program as well. Each of these little boxes is actually a div that the screen reader is going to skip right over. Okay, so I'm not actually here to just cast shade at a lot of Chi websites and SIGCHI websites, but these are nice examples of how common this is. Even communities that want to think about it and have the resources don't always realize the challenges that come up here. All right, so another type of problem that can occur is elements where you need non-standard mouse input events to interact with them. So here, there's a mouse over that's being listened for on the Amazon webpage in order to see some of the drop-down content. And that's not something that's usually going to be possible to generate using keyboard-only input. Okay. And it turns out the most common way that people deal with these types of accessibility gaps is just to ask a friend to help them. And that works from a completeness point of view. You can do that. But of course, it's not always going to be a favor that you can ask of somebody, and there's going to be a social cost to doing this. So you can imagine all the times that maybe you aren't supposed to be on the web, and if you had to ask your friend all the time to get you past these accessibility gaps, that would be quite onerous. Maybe like during talks. Okay, so the goal of this paper is to create tools that allow blind web users to overcome accessibility barriers on the web by handing off targeted visual interaction tasks to crowd workers on demand. And although crowdsourcing has been used to solve other visual accessibility problems, for example, by allowing remote crowd workers to answer visual questions about the real world, or through collaborative annotation, these conventions don't work well for the web because often we don't want to just actually get access to the information, but to perform some action on the web page itself. And prior architectures for shared browsing have been kind of all or nothing. So you give either complete control over your browsing experience to someone else or not. And that's not something that you're going to want in all cases when you're talking about personal web use. So in this paper, we introduced two systems, Arboretum and Arbility. I'm going to start off with by discussing Arboretum, which is an architecture for managed shared browsing. So Arboretum includes both a web client, which works like any other browser, and a web server that can present a managed clone to an end user's web page remotely. So this technique works for any web page, although if you follow the link at the end of this talk and check out the open source version, you'll notice that it doesn't work on some things like 3D canvases. Rest assured that's a quirk of the research prototype, not a limitation of the tool itself, or the approach itself. Okay, so to illustrate how the Arboretum client works, I'm going to show you how it works on a really simplified page that allows a user to type a message and either log out or submit. So one of the challenges here you'll see is that after they type their message, they can simply click one of these two buttons. But if you do this with a screen reader, there we go. It turns out you cannot actually tab over the logout button, so you can't select, you can't select the submit button, and the logout button actually listens for a mouse down event, which not every screen reader is actually going to emit. Let's have a key press. So our goal is going to be to allow blind users to seamlessly hand off this page in order to accomplish their goal. And the first thing we need to be able to do is hook the internals of the web browser here. So what we're going to do is use Chrome's DevTools protocol, which is usually meant for creating debugging tools for developers, but instead use that to hook into the end user's page and then serve up those pages that look like serve up a version of those pages that look like the original to remote helpers. And this could be one or more remote helper. Okay. So behind every web page, there's a DOM tree that encodes all of the information on the page, where we have a set of DOM elements that correspond to elements on the web page itself. So in order to create a simulated page, we're going to have to be able to make a copy of the entire DOM, but then look at things like references to JavaScript and make sure we remove those. Look at things like this on-click handler, we're going to remove the event handler and then replace this with the code that pings the Arboretum server whenever someone clicks the element. And then we're going to have to take resources like images and replace their URLs with a local resource indicator. So this means that things that are behind a login or a paywall or IP wall will still be accessible for remote users as long as they're accessible to the end user. So you also have many pages that specify their layouts using CSS. So we'll have to take things like CSS pointers and again replace them with these resource IDs. And Arboretum will allow that, or manage that entire process. Okay. In addition, so when a remote user's web browser asks for content of a style sheet, it again is going to modify all of these references inside of the style sheet and point to the Arboretum server instead. So this process is done recursively, which makes sure that all pages and pages contained within them are handled. And for any contained content, Arboretum replaces references to point to the Arboretum server and instead can simulate a version of that frame's content to avoid cross-site issues. Okay. There's also information not in the DOM hierarchy that syncs between clients. For example, the text content in this input box is not part of the DOM, but Arboretum is going to keep it synchronized anyway. Okay, and I'm going to skip through a little bit of this because I'm running behind. So this is what it looks like in action. If you see the person typing on one side, it's actually syncing the content across the different pages. And it looks exactly the same on both. But there are some asymmetries. When the end user here clicks log out, that updates the state of both web pages. However, when the remote worker clicks log out, they don't have the ability to unilaterally take that action. That's registered on the server, and we can do something like either aggregate or hand back, as you'll see in the future example, the decision to the end user. Okay, so that's Arboretum. And now I'm going to talk about Arbility, which is as a shared chat room and the ability to propose actions back to end users so that we can help blind users hand off targeted visual interaction tasks. So here's a video of Arbility in action. Somebody's typing in a message to a remote helper to make their request. And then that is fielded by the remote helper. And they can actually perform some action. The system automatically captures that and then makes it an available option to the end user. So that'll show up like this. And they can accept or reject the proposed action or ask for more information. And as soon as they accept that action, the state is updated. Okay. And as this progresses, you can do this for each potential action. And you finally reach the state that you wanted. Finally, when the session is done, the end user thanks CrowdWorker and closes the session, which then cuts off any remote links so that they're back to browsing alone. To evaluate this, we recruited nine blind participants and asked them to complete 3 different tasks that are representative of inaccessible web pages. We reused tasks from Bigham et al.'s paper, The Effects of Not Knowing What You Don't Know to Web Accessibility. We picked only the examples that were considered difficult or impossible in that paper. And we performed this study remotely to allow people to use their own configuration in terms of their screen reader and things like that. All right, so in the first task, they had to find some visual information. In the original study that we were comparing to, 0 people were able to complete this task. 0 blind users were able to complete this task, but everyone who was sighted who tried to complete the task was able to complete it. A second task involved looking up information that required performing a mouse down action, whereas most screen readers produce a click. Again, in the comparison study, it was 63% blind users and 90% of sighted users were able to complete this. And finally, a selection task on a food menu where 14% of blind users were able to complete this task originally and 86% of sighted users. So comparing Arboretum here we see that, or Arbility here, we see that Arbility allows blind users to complete these tasks at about the same completion rate as sighted users. But there is a downside, so this takes significantly longer. And, but that's actually kind of a reasonable trade-off in many cases, right? It's a little bit slower, but you don't have this accessibility gap that would have prevented you from getting to the information or accessing the functionality previously. All right, so participants also expressed positive feedback in the post-study interviews. One participant said that the tasks they were asked to do are realistic and representative of the types of things that they encounter when browsing the web. Another participant also said it was great getting quick answers to questions and that Arbility could save them a lot of frustration. But participants also expressed some concerns about the type of help that Arbility enables, specifically one, that the tool looks like it might allow developers to avoid creating accessible content. So they don't actually want the web to get worse because we can bridge these gaps, which is a perfectly fair concern. And of course, there's a potential privacy concern with handing off control of your browsing experience to random people on the web. And in future work, we plan to explore how we could address some of these privacy concerns. One way is actually looking at hybrid intelligence approaches to this problem. So we have a HCOM paper last year that looks at how you can use combinations of humans and machines to do some privacy preservation, even in tasks that seem like they would require divulging that information. But not all solutions to privacy might be technical, right? You might actually have approaches that help train people on when they can use these approaches and when it's probably not appropriate. And then the other solution is actually to build better automatic solutions by creating macros as a result of the interaction that we observed using Arbility. So we can actually start to automate parts of the web so that maybe one person needs to do an interaction, but for the most part, we've now built a bridge that can generalize to other settings. So I think exploring these directions and helping bridge more and more of the accessibility gaps on the web is really exciting. And with that, I am happy to take questions.
Hi, Jeremy Werner from UC Berkeley. Great talk. So I like this approach of helping people get to kind of do tasks that they would otherwise be unable to do, but also some of those examples seem like the div example, for example, seems like, is this a deficiency in the screen reader technology? Why focus on kind of recruiting extra people to just be the bridge rather than making better technology to serve the people? Because if they do have this, then they wouldn't have to have that social or fiscal cost.
Yeah, right. No, it's a good point, right? So the challenge is that for any standards that you develop, people will then break those standards, right? So yeah, we could patch over just the div problem and say, well, you should read all divs. That's actually going to create a lot of other problems with how you're able to browse through web pages, and somebody will use a table as an input element or something in the future. It turns out to be really hard to match the additional work required to kind of an easy-to-do programming task, right? So it's a challenge to get developers to actually follow these guidelines. There are guidelines out there that will make sure that you actually create a page that is perfectly accessible to screen readers, and it just doesn't happen. So we're trying to bridge the practical gaps that occur.
Cool, thank you.
Mm-hmm. One more quick question.
Hi, my name is Vladimir, University of Manitoba. Thanks for bringing up this problem, first of all, because I can really relate to it, and second, I was wondering if you thought of any adding persistence layer, for example, so that if you have a very typical problem people cannot click submit because it's a div, using the input from the first helper to somehow tweak the DOM, maybe through the layer of extension to help other people being able to navigate to this element through keyboard.
Yeah, no, that's a very good point. I think so one of the nice things here is that we're able to actually capture a lot of the information that's happening during the interaction on the server side, which we wouldn't necessarily see from a typical hosted web page when we have users interacting. And so what we've been looking at is how you generate scripts that can then be reused to bridge these gaps. But it's interesting to think more about how we could actually modify the page more deeply and maybe even generate best practice snippets out of that. But
thanks.
Great. Thanks.
All right, let's